Hello, my name is Zach Willis, and welcome to my advanced energy presentation about Flywheel energy storage. Renewable energy sources are intermittent by nature. For example, a solar panel array could experience cloud cover, or a wind generation system could experience a lull in the wind. What do we do about this? How can we fix it? One method is to take the excess energy, store it in a mechanical system, and when we experience these events, to convert it back to electricity to supply the grid. This is done by a flywheel energy storage system. So what is a flywheel? It's one of the oldest energy storage devices that man has used. And an example of this is the potter's wheel. So there's a rotating mass to maintain a constant circular motion with intermittent energy input. You can see here the user would input energy with their left leg, cause the flywheel to carry it through the revolution until more energy is input. They're simple and reliable because all they are is a rotating mass on an axis, and nowadays we typically use them on reciprocating machines to smooth motion. So for example, in an internal combustion engine, it will carry the pistons through the intake, exhaust, and compression stroke until energy is input with a combustion stroke. So how do flywheels store energy? They absorb energy as speed increases, and they release energy as speed decreases. And you can see that in the equation here. This is the equation for energy stored in a flywheel. So its energy is equal to 1/2 the moment of inertia times the rotational velocity squared. So the first thing to notice is that rotational velocity, or you can think about it as speed, is squared. So if you double your speed, you're going to quadruple your energy stored in the flywheel. So we want the flywheel to spin as fast as possible. Now, moment of inertia is just a measurement of how much that flywheel wants to stay in motion. It's just a quantifiable way to measure the inertia. And that is composed of an inertial constant, which is based on the geometry or the shape of the flywheel. So if it's a rim type like we saw before, the constant is 1. For a cylinder, it's 0.5, and for a disk, it's 0.606. Typically, these large-scale installations are a cylinder. M is the mass, which is weight on Earth, and radius is the distance from the center to the outside. These flywheels have to be quite large radius, high-speed devices to store a lot of energy. So that brings us to how we store solar or wind energy mechanically. So we would couple the flywheel to a motor generator. A motor generator is a device that can act as a motor or a generator, which motors and generators are, for the most part, interchangeable if they have a permanent magnet rotor. So with a motor, you input electricity and you get motion out. With a generator, you input motion and you get electricity out. So during periods of peak production, we can take some of this excess energy, run the motor to input energy into the flywheel and spin it as fast as it's designed to go. And then later, during cloud cover or a lull in the wind for a wind installation, we can extract that energy by using the mass of the flywheel to rotate that as a generator and output energy to supplement what's on the grid. So what are the advantages of flywheel energy storage? They can be made very cheap. There's a French startup company that's using carbon fiber reinforced concrete as their flywheel material, and this dramatically reduces the cost per kilowatt hour for their installations. Other installations are made of steel. So the large-scale flywheels that are in use now are typically made of steel, and the device itself is 97% recyclable. They are reliable because they are simple. It's just a rotating mass. They're low maintenance for the same reason. And the most exciting part is they're capable of well over 100,000 full-depth discharge cycles. And if you compare that to a chemical battery, it's nowhere close. And there's no degradation when you go from full energy storage to no energy left in the device. So what are the disadvantages of flywheel energy storage? You have to maintain a vacuum. So this adds to the cost and complexity of the device, but it's done to minimize friction so that we can keep the mass spinning for longer with less losses. With a vacuum, even atmospheric pressure is relatively high, so high pressure always wants to lead to low pressure. So you have to constantly maintain this vacuum, and it also consumes a little bit of the energy from the grid to do that. Magnetic bearings are typically used, or electromagnetic bearings, and there are active magnetic bearings which use electromagnets to sense the or to correct the position of the shaft. Passive magnetic bearings use permanent magnets and don't have that capability. We're limited by size. So if you remember from the equation, two of the factors were radius and mass. So if we want a large scale installation, we would have to greatly increase the radius and the mass of the device. An alternative to that would be to spin it insanely fast. But there again, we're limited by the material properties that we use to create the flywheel. Oftentimes, carbon fiber is used because it can withstand those high forces and that high velocity. So now we're going to look at some installations to see how these have been practically used. So we can store energy during peak hours. We can use it to help stabilize the grid to maintain frequency or to compensate for large loads coming onto the grid. And they've also been suggested to be used in residential applications for energy storage from solar panel arrays. So this installation was done by a company called Amber Kinetics. It's in Massachusetts. It has a capacity of 512 kilowatt hours, which is pretty impressive. It's used to reduce peak load on the plant and increase the reliability of the solar panel array. So this is a top-down view of another installation by the same company, Amber Kinetics, and this is in Hawaii. So they actually utilize a lot of solar and wind energy in Hawaii. And this installation is a 32 kilowatt hour installation. And what you can see there is that this can power 25 homes for up to 1 hour. So if there's a storm or something like that, this can be used to supplement the existing renewable infrastructure. And you can also see that it's quite large. I mean, 5 tons, which it would have to be large to store a large amount of energy, as we talked about before. But another exciting thing is the 30-year life. So high reliability, simple operation, and it lasts. And when it doesn't last, it's 98% recyclable. This application is actually the one that excites me the most. It's a French startup, and they're the company that's using the concrete flywheels reinforced with carbon fiber. Currently, their capacity is about 10 kilowatt hours, but their goal is a 50 kilowatt hour installation, which could run an entire home for a day. I hope you've learned something and have enjoyed my presentation. I just wanted to say I've enjoyed being in this class and interacting with each of you. Thank you very much.